looking, it looked like some of us didn't get the syllabus sign-in sheet into the Dropbox. It seemed like we're still showing we're short a few submissions. If that's you, just go ahead and submit it late. I'll extend the due date through tomorrow or whatever if you still need a chance to get it figured out, but make yourself a little note if that's you that didn't do the syllabus sign-in sheet to make sure you do that tonight. Okay? So just a little bit of courtesy for you guys. Joe, will you grab the light for us?
Yeah.
Thanks. So today we're going to start really kind of talking about mathematics here in detail. So I'm going to do the notes here in OneNote. And what I've done here is I'm putting these notes inside of the content library on OneNote. So if you wanted to look at these later, exactly what I've written as I've written it in OneNote, they're available. Now you won't be able to watch it live on your computer because it takes time to get, for my computer to send this information up to the cloud and then time for your computer to pull that information back from the cloud. But by the time you leave class and if you were to look at it like next hour, everything will be there, but you can't just watch it live happen. In addition, I am recording this lesson. So again, if you space out or you go, oh, I took some notes, but like he said something here and I think I missed it and it seemed like it was important, I don't know what to do with the homework or any kind of thing like that, you can come back and watch the video, and they're just YouTube links, so you can jump ahead or whatever you need to kind of get to that. So again, if you want to take physical notes, if that helps you pay attention, you're welcome to do that. If you'd rather like sit and listen and pay attention because you know that you have my notes already, that's fine as well. I just trust that either way we're being attentive and non-disruptive, and you're doing your best to kind of follow along and pay attention. During the course of this, if I happen to say something or write something down or use a symbol or my penmanship is bad and you can't read something, please stop me, okay? I am happy to go back and to re-explain things and to reiterate and, try to write neater and all that. Everybody okay with that plan? Okay. So we're going to, oops. Come on now. There we go. All right. So we're going to start just with a little bit of having you guys think back to your Algebra 1 experience. So I know that was a long time for some of us, right? We had a year of geometry probably sandwiched in between. So it's been a little bit of time, but it's going to kind of help me figure out what it is that you guys did and what you remembered, and help you guys get an idea of kind of what my expectations would be in terms of things that you kind of can do still, okay? So there's no wrong answers to this, and if somebody says something that they remember doing in Algebra 1 and you're like, I didn't do that in Algebra 1, that's okay. And I know that certainly everybody's Algebra 1 experience won't be identical, depending on like how fast your class was able to move and all that kind of thing. Like some of us may have done topics that other people are like, I don't even know what that thing is. And that's okay. It doesn't mean you're behind. Okay with that? All right. So when we ask you to think back about what you guys did in your Algebra 1 class, what's one thing that you guys remember doing or spending a lot of time with? Again, there's no wrong answers to this. So just kind of think back and think about what Algebra 1 was like. What are some things that you ended up doing? And even if you don't know a name for it, if you can kind of describe it, we'll come up with a good name for what it is you're describing. So again, if your vocabulary at 8 in the morning isn't great in terms of math, vocabulary. That's okay. We'll figure it out together. Yes, sir. Okay. Yep. And if you're not familiar with that, that's an acronym that's describing the order of operations that says parentheses, exponents, multiplication, division, addition, subtraction. Some places put an O here for operation because there are other operations other than exponent. For example, square roots happen in that spot. So depending on who, presented that acronym to you, they may have used an O there instead of an E. Either is fine, but certainly you would have spent some time in your Algebra 1 course talking about the order of operations. That's a really important idea that you're familiar with, and it's my expectation that everybody is familiar to some extent that there is an order of operations, that some operations come before others unless there's like a parenthesis telling you to do something first. Now my expectation is not that you can do this flawlessly all the time. Not unsurprisingly will expect some mistakes to be made here and there, but there are situations where once we've kind of pointed out what the mistake is, hopefully it's something that you're comfortable correcting in the future, right? I understand that maybe some refresh needs to happen and some mistakes happen to time, but with pointing out that there's a mistake should be capable of fixing that going forward and not making the same mistake on order of operations over and over and over again. Okay? Good. So that's absolutely something you would have spent some time on. What else? Go ahead. Factoring. Fantastic. So there's probably a couple different types of factoring that we talked about in your Algebra 1 course. So one type would be like a greatest common factor. So for example, if you had 3x squared plus 2x, notice that each of those terms has a factor in common, that factor in common being x, right? So you could write this as x times the quantity, 3x plus 2. Where this greatest common factor type of factoring is basically just the distributive property in reverse, right? So the end result after a greatest common factor is something that looks like a distributive property, right? Where you have a monomial times some kind of polynomial, right? Good. There's another type of factoring that some of us may have seen. And this is probably the type of factoring, when you said factoring, that you were thinking of, because the greatest common factoring is something you surely spent some time on in Algebra 1, and I expect that we are comfortable doing that. My suspicion would be maybe like a half to 2/3 of us spent time factoring quadratics. And really, I would say quadratic trinomials in your Algebra 1 class. So an example of that might be x squared plus 4x plus 3 that we can factor to x plus 3 times x plus 1. Now, I didn't explain at all how we did that factoring, and if you're like, I remember doing that, but I don't remember how to do it, that's okay. If you do remember doing that and how to do that, that's fantastic. My suspicion is that, a half to maybe 2/3 of us did this in our Algebra 1 class. If you didn't, that doesn't mean that you're behind. We will do the heck out of this same skill over again in this course, because it is a foundational skill moving forward and something that's really, really important. Yes, sir.
So I think I might have looked like the and
okay. As long as you can see to plug in?
Yeah.
Yeah, that's fine.
Okay, thank you.
Mm-hmm. Okay, so just quick show of hands. How many of us remember doing this kind of factoring, like factoring a trinomial in your Algebra 1 class? Raise them high so I can get an idea. Okay, so it's about right. So around a half, it looks like, remember kind of doing this. And if your Algebra 1 class covered a lot of material and was able to go and do a lot of things, you might have even factored quadratics that looked like this, where the leading coefficient wasn't 1. This is even a little bit more tricky. Again, not an expectation that you come in with that particular skill, because we will handle this situation as well, and we'll do a lot of practice on it. But some of us might have remembered doing this in our Algebra 1 class. This would be rare. My expectation would be that just like a handful of us remember doing this in our Algebra 1 class, but some of us might have. Since we were on the topic of factoring, I figured I'd cover, the most common cases of things that we would see in our Algebra 1 class. But these two skills, we will do these again. Okay? And I might present them. The method I'll present might be a little different than what you learned to start with in your Algebra 1 class. But what I'm going to present to you is the most general method, rather than starting at the special case, which is probably what you guys were presented with in your Algebra 1 class. So we'll eventually narrow down to that special case, but we're going to start with the method that's going to work all the time for all quadratic trinomials. And then talk about, okay, when's the case where I can really use the shortcut and do this quickly in my head? But we want to start with the most general case, because the shortcut doesn't always work. But we'll get to that. That'll probably be towards the middle end of first semester, we'll get to factoring and do that in quite a bit of detail. Good. What else do you guys remember? Yes. What? FOIL. Great. So FOIL is another acronym, and it just describes how you multiply two binomials together. So it says we multiply the first things together, and then the outside things together, and then the inside things together, and then the last things together. And when we combine our like terms, we're left with a quadratic polynomial in most cases. Now, if your binomials weren't linear like they were in this case, you could end up with a higher degree polynomial than a quadratic, but we will do some foiling, and we'll extend this idea of polynomial multiplication also in this semester to deal with situations where maybe we don't just multiply two binomials together, but we multiply something with 3 or 4 terms times something with 3 or 4 terms. And what's a way to deal with that that's at least easy to keep track of everything going on? Because as you imagine, if you multiply two 4-term polynomials, that's a lot of things to keep track of, right? You have 16 multiplications to kind of keep track of, and it becomes a little bit difficult to kind of make sure that you've done multiplied all the terms together and then keep track of all the terms that you've multiplied out. But we'll talk about ways to do that. My expectation is that just about all of us remember doing foiling to some extent as an Algebra 1 topic. This is something that I think almost all Algebra 1 classes would have spent some time doing, and it's an easy one to remember. The acronym helps students remember doing this typically. I want to point out to you what you may not have noticed is that if you look at factoring and you look at foiling, they're literally the opposite processes, right? Factoring is basically undoing foiling, or foiling undoes factoring, right? So they just transfer back and forth between two different representations of the same polynomial. And this is really common in mathematics. One of the things we really like to be able to do is to take something like a polynomial and find different ways that we can represent it and talk about the ways in which we can go back and forth between these different representations. because these different representations can tell us information about the polynomial really easily that maybe the other representation can't. So it's very helpful to be able to move back and forth between these different representations. Okay, good. So foiling, absolutely. And we'll kind of extend this idea of foiling. So we'll start with FOIL, but we'll build out past that and do some more complicated things than what I would consider just FOIL. Good. What else do you guys remember? There's a couple of major topics that I'm sure once we say, everybody's going to go, oh, yeah. How about graphing a line? How many of you spent times graphing the equation of a line in your Algebra 1 class, right? You probably spent the majority of one semester doing topics related to writing the equation for a line or graphing a line and the different ways to graph a line and slopes and all that stuff, right? That is the most common, I think, in my experience of teaching this class, response that I get from students is talking about graphing a line or writing the equation for a line. Right? How many of us remember getting 2 points and being asked to write the equation of the line that passes through those 2 points? It's a very common Algebra 1 question, right? The expectation there would be that, most or all of us remember kind of doing that particular skill. What else here? So in terms of this class, we'll talk about a lot of functions other than just linear functions, like equations that graph things other than lines. So we'll spend a lot of time graphing, not necessarily graphing a line, and talk about the procedure that we can use to graph these different types of functions. And just like writing the equation for a line, we'll be interested in writing the equation for, a polynomial or a logarithmic function or blah, 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 that passes through certain points. And we'll talk about how to do that as well. So we're going to take kind of the same idea, the same task, but we'll apply it to different situations. And the procedure is going to change quite a bit in those sort of situations. But we'll talk about that when we come to it. But that type of a skill, writing an equation to describe a situation, is a really common mathematics skill. It's something that's quite useful, and we spend a good amount of time talking about. Not necessarily in the linear setting like we have here. But, what else? Okay, well, we'll stop here since it seems like you guys are out of inputs, and that's okay. It is 8 o'clock in the morning, and it is from a course that was over a year, like 2 years ago, really, the start of that course. So if this is what we remember, that's okay. I don't want to, tip the scales too much. So we're going to start here today talking about Algebra 2. Or your second year algebra course. I mean, we call it Algebra 3, 4 here or whatever. It's the second year algebra course, however you want to title it. And what we're going to start with is talking about kind of the fundamental algebraic object. So when you talk about algebra and you ask me, what's the fundamental thing we use algebra with? What would you answer that? Yes, sir.
Solving equations.
Okay, so that's a skill, and absolutely it's a skill we use algebra on, but I'm talking about an object rather than a skill. So what's our fundamental mathematical object in the algebra classroom? it's tempting to think numbers, right? Like that's what we use mathematics on. A number, though, contrary to kind of how we've thought about it to this point, isn't so much an object. A number is an adjective. It's describing something. Our fundamental object in our mathematics classroom is actually a set. And you probably have not even heard this up until this point, but that's what our fundamental mathematical object is called a set. So let's define what a set is. So a set is just a list of mathematical objects. So when we talk about a mathematical object, like numbers or ordered pairs, or it could be a function or an equation or, a vector, if you don't remember those from geometry, or you could talk about sets of shapes. You could talk about all the sets of triangles that are similar to some specific triangle. It doesn't really matter. The point of a set, though, is that no object repeats. So nothing in your list is listed more than once. So, for example, just to talk about some notation. So when we talk about notation, what we mean is like the symbols that we use to kind of notate something, to describe what this thing is. So when we talk about a set, typically we use a capital letter. So I'm going to use the capital letter A to describe my set. And then there's lots of different ways we can describe our set. One of the most common ways is that we're going to use these curly brackets. So we're going to draw a set of curly brackets like this to indicate that what we're listing now is a set and not something else. And then if our set is short, we can just list the things that are inside of our set. So if our set is just the numbers between 1 and 10, or I should say the integers between 1 and 10, we can just literally write them down in a list. We call this type of set a discrete set because the number of things inside that set is finite. So there are exactly 10 things in that set. You can count them up and you could finish. Okay with that idea? Let's call that, it would be more accurate to call it a finite set. Let's do that. Sorry about that. So that's just describing the set of, the most common counting numbers, right? If I asked you to count to 10, these are the numbers you'd need. But if I wanted all the numbers between 1 and 10, what would that list look like? Would it be the same list? What about 1.5? Or 1.07? Or 2.65328? Would I ever be able to finish a list if I wanted to list all the numbers between 1 and 10? No, right? That list is going to go on and on forever because we can keep making our decimal longer and longer and longer. and adding numbers to the end of our decimal, and you can never finish, right? Everybody's okay with that idea? Okay. So the way we wrote our set for A, where we just wanted the counting numbers between 1 and 10, can't be the same way we write the set for B, where we want all the numbers between 1 and 10. We're going to have to use a slightly different method to do that, because we can't just list them exhaustively, because there's an infinite number of them. Okay, well, this is what we're going to do. We're going to start with our set bracket here anyways. And then we're going to describe what this set looks like symbolically. So I'm going to say my set is going to contain just a single thing, and what I'll call x. And then I'm going to put this colon here. This colon is just kind of a mathematics abbreviation that stands for such that. So now I'm going to describe a rule to describe these x's. So if I want my x's to be all the numbers between 1 and 10, I can write that as an inequality, right? I can say 1 has to be less than or equal to x, and then that has to be less than or equal to 10. This is an example of an infinite set. Typically, when we describe an infinite set, we describe it with a rule. And in this class, that rule would most often take the form of some kind of inequality. Since there's an infinite number of things, I can't list them all. I'm going to just say, okay, that infinite number of things just have to, I want all the things that obey this rule. Because I can write the rule down, right? But I can't list them all, because I would spend my entire life listing and never really even finish. I couldn't even get all the things between 1 and 2 in my lifetime. Or as many lifetimes as you wanted. We could all devote our entire lives trying to do this and would never finish. Rather frustrating, right? So we have to find a way around that, and the way that we're going to get around having an infinite list to record is, instead of recording an infinite list, we're going to just describe what the things on that list look like. So it's saying everything in between these two numbers. Okay, that's clear, right? We don't have to list all of them explicitly to understand what's in there and what's not. Do we feel okay with this set? Okay. So let's do an example then. Let's say that A is the set So this symbol in between the 2 and the A is like a curvy E. This is another just piece of notation. In mathematics, what that says is, or we read that as a member of. So we're asking, is 2 a member of the set A? What do you guys think? Yes, right? We can see it. It's right there, right? If we asked, is 1 a member of the set A, we would say, no, right? It's not. If I look at my set, I just have the number 0, 2, 4, 6, 8, 10. 1 is not in there. Even though it's a digit in the number 10, it doesn't count. Everybody's good? Okay. Let's say we then have this set. Let's not do that quite yet. So, is 2 a member? Oops, not A. We are talking about B. Yes. Why do you say yes? That's correct. Good, because 2 is between 1 and 5, right? Okay. Is 1? Yes. Okay. How about is 5? Yeah, so notice the difference between the inequality symbols there. 1 is included in B because it's a less than or equal to. 5 is not included in B because it's a strict less than symbol, right? So be a little bit cautious there. Do you guys all remember the inequality symbols, though? Yes. Okay. Yes, sir. So x is the numbers between 1 and 5. So 2 is one of the numbers between 1 and 5, right? So this is saying x has to be greater than or equal to 1, which 2 is, and x has to be less than 5, which 2 also is. Because it satisfies both parts of that inequality, 2 would be in that set. Does that make sense? Okay. Does everybody feel okay with this idea of set membership? Okay. So we're going to talk about some common sets now. The first one is going to be called the natural numbers. And because these sets are common, we're going to give them little symbols to abbreviate them because we use them on a kind of a regular basis in our mathematics class. So the symbol for the natural numbers is like an N with like 2 bars on the diagonal. So the natural numbers is the set 0, 1, 2, 3, ... Do we remember what this ... means? Means it kind of continues on forever in the same pattern, right? That ... has a name. It's called an ellipsis. Ellipsis, I think is how you spell that. Can't remember if it's 1 L or 2 L's. Now, a weird thing about mathematics is there's no consensus on what the set of the natural numbers is. So depending on the context, some people say the natural numbers include 0 and some say it does not. In a high school mathematics setting, this is probably it's probably the definition I would assume. Although in practice in mathematics, this is probably the one that we're using more often, just because of the way the natural numbers end up being used. But that little detail is not something I would spend a ton of time focusing on. Just wanted to make you aware in case you did some Googling and you're like, hey, this says the natural numbers don't include 0. You know, like what gives? Well, it's fine. Okay. The next one, or the next set, is called the integers. And the special symbol we use for the integers is the letter Z, but we put an extra bar on that diagonal. You might think to yourself, why the heck did we come up with the letter Z for integers? Well, this notation comes from Germany. The Germans did a lot of very important mathematics, especially in the field of algebra in the 17 and 1800s, and are still a very important nation from a mathematics standpoint. And the German word for integer starts with Z. That's why the symbol is still Z. Since we're an IB school, I figured I'd mention that. So the integers includes all the negative whole numbers. It includes 0, and it includes all the positive whole numbers. So I have an ellipsis going at both ends, right? Those negative numbers keep getting smaller and smaller and smaller, and the positive numbers keep getting bigger and bigger and bigger. Should I number these? Let's number them. 1, 2, 2, 3. Okay. Our next set is the rational numbers. And the symbol we use for the rational numbers is this letter Q, but we put this extra little vertical bar in it. So this definition for Q looks a little cryptic, right? It's a little hard to parse what exactly this means. But we're familiar enough with this notation that we should be able to kind of decipher this. So remember, this is like the notation for an infinite set. So it tells us what the things in our infinite set look like. They should look like some kind of fraction, like a P over a Q. Everybody's okay with that idea? Okay. And then it describes kind of what these P's and Q's are then. So this is such that and then it says P and Q are integers. And q is not 0. Okay, so name two integers where the second one isn't 0. Somebody. Doesn't really matter. Just say a number. 3. Great. And then let's pick a number for q. It's not 0. 4. So that tells us that 3/4 then should be a member of the rational numbers. Does everybody kind of see what we're getting at here? Yes, sir. Of course. Yes, sir. 0. Sorry about that. Thank you for asking. Again, if you can't read my crummy penmanship, please let me know. I don't think it's that bad, but sometimes it's different enough from yours that you're just not ready for it or familiar with it. But again, important that you can read what I've written down. So when we talk about these rational numbers, what are we really talking about? We're just talking about fractions, right? That's it. We're just talking about a fraction. Here's an aside question. Can every number be written as a fraction? So I've seen some people say yes. I've seen some people shake their head no. The answer is actually no. There are some numbers that we cannot write as fractions, and one of them, I promise you, that you are well familiar with, that you learned a lot about last year in your geometry class. Anybody take a stab as what that number might be? Pi is the correct answer. Another example is the square root of 2. Also cannot be written as a fraction. In fact, the square roots of anything that doesn't reduce down to an integer, like the square root of 4, we can write as a fraction because the square root of 4 is just 2. But the square root of 3, the square root of 5, the square root of 6, the square root of 7, the square root of 8, not the square root of 9, but the square root of 10, 11, 12, 13, 14, 15, not 16, 17, 18, etc. All of these things we can't write as fractions. Now you can come very close to a fraction to approximate these things. Like way back in the day, we used 22 over 7 as an approximation for pi when you didn't have pi programmed into your calculator. There was a time where that wasn't the case. This is a little bit better than 3.14. But if you were old enough, you had calculators where pi wasn't programmed in there, or at least, again, you don't have the entire pi programmed in your calculator, but it's like 100 decimal places of it to where it's like nobody cares. Like your answer is good enough for anything. But it's still just an approximation. So there are some numbers here that we can't write as fractions. Now here's a question for you. Which one do you think there's more of? The numbers we can write as fractions or the numbers we cannot? Now, who says they're the same? That would be a reasonable response, since you can fairly say there's an infinite number of both of them. Here's a weird thing that probably most of us didn't know. There's actually different sizes to infinity. Let me explain. This is a complete aside, not something I'd ever expect you to regurgitate for me on a test or a quiz. Okay, this is just purely because it's kind of fun and interesting. Okay, so let's say we have the natural numbers versus the integers. There's an infinite number of both of them, right? Because they both keep on going. But it seems like the integers, there should be more of, a bigger infinity, because you have all the natural numbers, and then you have negatives of all the natural numbers. It seems naturally that there should be twice as many, right? There's actually the same amount. And the way we can show that is if we can show that there's a mapping from one set to the other that's 1 to 1. So everything from one set pairs with exactly one thing in the other set. And it's onto, meaning that everything from this set is used and everything from the other set is used. So if I can show everything is used on both sides and they only match up one time each, they must have the same number of things, right? Does that make sense? So what we do is we say from the natural numbers, we take the odds and we map those to the negatives. And we take the evens and we map those to the positives. There's an infinite number of odds, so I can get the infinite number of negatives, right? And there's an infinite number of evens, so I can get to the infinite number of positives in the integer, so I've covered everything with one number exactly each way. Does that? And I skipped a lot of details there because, again, this is just because it's kind of neat and interesting. But does this make sense? At least how we're kind of doing that pairing to show that, like, okay, we have two things that are infinite size. How do we show they're the same infinite, same size infinite? If we try to do the same thing, though, for the rational, well, if we do the same thing for the rational numbers versus the integers, these are also the same. It's much trickier, the mapping that we do there. It involves like making a two-dimensional grid of the integers and like pairing things up and like crossing out all the things that are like really just a reducible fraction and doing like a zigzag through it, but it's possible. It's way beyond the scope of this class. A fellow named Cantor, a mathematician whose last name is Cantor, actually did this. He's actually like a very famous, well-known mathematician. But his proof for this is one that's quite famous and is kind of the standard proof of this. But if you talk about the rational numbers versus the things that are not rational numbers, this symbol here is the complement, is what this means. And it basically just means not. So when I put the bar over top of a set, we're talking about the things that are not in that set. So here we have the things that are not able to be written as fractions. This is actually not the same. And it turns out that the things that are not fractions, there's a bigger infinity of. There's no way to map the fractions onto not the fractions. And the issue is, if we think about this, if we just talk about the stuff in between 0 and 1, How many things are there? There's infinite decimal numbers in between 0 and 1, right? If I try to take my fractions that there's an infinite of and try to map them up inside of just that little section, still can't even do that. And the reason has to do with like the decimal expansions. So the typical way you'd prove this is using like a contradiction. Maybe you did this in geometry. Did you do proof by contradiction in geometry? It would have been like one day, so if you've forgotten, that's okay. But the way a proof by contradiction works is you assume whatever you're trying to prove is true, and then, or the opposite of what you're trying to prove is true, and then using that, you try to make something nonsensical happen, right? Like, I don't know, like I can't think of a good, easy example in like a real world setting. Okay. So like, want to prove to you whether it's raining or not, right? If I'm trying to prove that it's not raining, I'll say, well, assume it is raining. If I go outside, then I should be getting wet. But I went outside and I didn't get wet. So it can't be raining, right? That's the idea, is you're just assuming the opposite of whatever you're trying to prove is true and show that something nonsensical happens that breaks some other rule. So the idea would be, is if you write out all the, is you assume that there is like a, how do I want to say this? You know what? Like, this is getting way too complicated. It doesn't matter. The fact is that there's more of these than the other. I'm getting way too complicated for this class. So let's just stop here. And this is, again, a complete aside. You don't need to really know this. I just think it's kind of interesting. And we're on the first day, and I'm not trying to cover too much material. I just want to kind of talk about mathematics a little bit here. All right. So back to our list, right? What were we on? 4? Yeah. Okay. So 4 is called the real numbers. And the symbol we use for that is this capital R with a second vertical bar on it. So R is basically any number, or the real numbers are anything that can be written as a decimal. So basically that includes everything that you know about to this point, right? Because even those things that you can't write as fractions, you can write as a decimal, right? Like pi's 3.1415, yada, 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 goes on forever. That's okay. It can be written as a decimal. It's an infinite decimal. It doesn't really end, but it has a decimal representation to it that's unique, right? Okay. There's actually a fifth thing called the complex numbers that I would guess that maybe only a handful of us have heard mention of. And again, the symbol for the complex numbers is the letter C, and then we put an extra little vertical bar inside of that C. So the complex numbers are things of the form a plus bi, where a and b are real numbers, And I is the square root of -1. We call I the imaginary number. And I'm guessing maybe one or two of us have heard about I being the imaginary number, maybe in your Algebra 1 class. If you haven't, that's okay. We'll cover that in great detail much later on. This is just kind of talking about these common sets. And this is one we'll talk about in this class, so I'm just going to kind of mention it now. Again, I don't expect you to know beans about it other than like its symbol is this C thing. And then this relationship that we're going to talk about in a second. Okay. So, if we look at these 5 sets, and you go back and you look at their little definitions that we wrote out, do you notice anything in common between them? Let's start specifically with just the natural numbers and the integers. Yes, sir.
But they both use the ellipse.
Okay, they both have an ellipsis in it. Absolutely. What else do we have? Look at the specific numbers there. Yes. They're all whole numbers? Sure. Absolutely. Look at everything in the natural numbers, and then ask yourself, is this also an integer? It is, right? Everything in the natural numbers is also a member of the integers, right? We call that relationship a subset. And the symbol that we use is like a less than symbol, but it has a curve end instead of a pointy end. So we'd say A is a subset of B if everything in A is also in B. Okay with that idea? So if we compare the natural numbers and the integers, we say that the natural numbers are a subset of the integers because everything in the natural numbers is also in the integers. Everybody's okay there? Let's look at the integers and the rational numbers now and ask ourselves the same question. Is everything in the integers also in the rational numbers? Remember, the rational numbers are just fractions, right? Can I take every integer and write as a fraction? Yes, right? How can I write 7 as a fraction? 7 over 1. How can I write -5 as a fraction? Negative 5 over 1. How can I write 0 as a fraction? Not 0 over 0. 0 over 1. 0 over anything other than 0 is 0. 0 over 0 is undefined. Anything over 0 is undefined. But what this comes down to is anything in the integers I can write as a fraction, which means that the integers are a subset of the natural numbers. And that also means then that integers are a subset of the rational numbers, which means that the natural numbers are also a subset of the rational numbers. Everybody's okay with that? Because that subset's going to continue all the way down, right? Like if A is a subset of B and B is a subset of C, then A is also a subset of C, right? Okay. And now let's look at the real numbers and the rational numbers. Remember that the rational numbers are the fractions, and the real numbers are anything that has a decimal expansion to it. Can I write every fraction as a decimal? Sure, absolutely. How do I do that? You just do the division, like the long division. It'll give you the decimal, right? So what's that tell me? That every rational number is also a real number. Okay? And then we have one more pair to look at. Let's go back and look at our definition for C. So A and B are real numbers, right? If B is 0, what's going to happen? Then you would just have A plus 0i. And what's 0 times anything? 0. And what's anything plus 0? Itself, right? So that's just going to be A. Everybody agree with that? And what's A? Just a real number, right? So are the real numbers contained in the complex numbers? Absolutely. Absolutely. I'm sorry, what? Sure. This is just a messy equal sign. So if we wanted to draw a visual picture, sometimes it's fun to like visualize sets. Which one is going to be the smallest one? It's going to start on the left-hand side, right? That's going to be the smallest one in our picture. And then we have the integers. And then the rational numbers. And then the real numbers. And then the complex numbers. To kind of give you an idea of visually what this is looking like, right? Everybody's okay with this idea? So I want to point something else about this nice relationship that we have here. So let's go all the way back to like kindergarten. When you started kindergarten and you started math, what kind of things did you do in kindergarten math class? What's the number one skill we were worried about in like kindergarten math class? Counting, right? We started with counting. So what set of numbers did we need for counting? Just the natural numbers, right? Everybody agree with that? We can do all the counting we want with the natural numbers. Okay? And you go to first grade and second grade, and what did you start learning in those grades? So from counting, you moved into addition and subtraction. Now addition, no problem. If you had just the natural numbers, you can do all the adding you want, right? Where was the problem? Subtraction, right? If you did 3 minus 4, you don't have a natural number for that. So what do? We extend the natural numbers so that we can do those kind of subtraction problems. So now we're working with integers, right? And you continue going on doing integers. What's the next skill you start learning? Multiplication. Do you need anything more than the integers to do multiplication? No. What did you do after multiplication? Division. Does that do we run into a problem there? Yes, right? If we'd want to do like 5 divided by 4, my answer is no longer an integer. So what do I need? I need the rational numbers, right? Everybody's okay with this? So we extended out our integers to include the natural numbers so that we can do these division problems. Okay? So we go ahead and do that. And now you're starting to run into algebra, right? You've done it counting, addition, subtraction, multiplication, division. Now we're running into algebra. So we're doing things like solving, right? If you wanted to solve like x squared equals 2, what's going to happen there? Your answer would be the square root of 2, right? Is that a fraction? That was one of the things on our list that we said can't be written as a fraction. So what do we need to do? We extend that set again into the real numbers so that we can solve those kinds of problems, right? Everybody's okay with me? Okay, so let's say instead of solving x squared equals 2, we want to solve x squared equals negative 2. When I take the square root of a negative number, that doesn't work, right? So what do? We define a new number to represent the square root of a negative, and we extend our number set to get to the complex numbers. And this is where our extension kind of ends. But it brings to mind the idea of whether mathematics, is this discovered or is this invented? Did these numbers always exist, or did we create them so we could do these kinds of problems? I don't know, right? But it's an interesting philosophical question of whether this stuff was always there, or did we create this? I'm of the mind that this is the greatest human creation in the history of mankind, is mathematics. Is it allows you to describe the world around you in such excruciating detail and predict what will happen in the future in a way that really you would be unable to in any other fashion. It's kind of fantastic, but we did this as human beings, as a species. We've done this over the course of several thousand years, and it's kind of amazing that you went from this very simple idea of counting and built all this mathematics out and invented all these little ways in which maybe we get stuck. Yes, sir? Well, if you know... Okay, so like if I am going to throw a baseball and I want to predict where it's going to land, if I know how hard I'm throwing it and the angle that I'm throwing it and the way the wind is blowing, I can predict exactly where that should fall, right? So that's what I mean by predicting the future, right? Is if we know what's going on now, can we predict what's going to happen later? And in most cases, or in a lot of cases, yeah, we can, right? Or if, like, I flick this light switch, what's going to happen afterwards? Right? The light should turn on, right? Or if I push the power button on my computer, the computer's going to turn on. Describing what's going to happen next like to make that happen was all designed using mathematics, right? Like it's not just we fiddled around with this until we got it to work. In some cases, like people did that, but you know, like something, a system as complex as a computer, like you are not doing that just fiddling around. You have to have a clear idea of like how electronics work, and predicting how electronics work and describing how they work is all really done from a mathematics standpoint. You have laws describe like how electrical current moves and blah, 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 blah. Like how a computer operates is actually, you know, is a really, really complicated problem. Well beyond the scope of really any high school class when you talk about it from that standpoint. But it allows, you know, like having that language allows you to create machines that are incredibly complex, that can do fantastic tasks. All right. So let's stop here. I don't have any assignment for you today because we haven't really done anything other than like some definitions, but that's okay. I'm happy with how today went and what we're